Okay, we're here to talk about SRv6+. We've already talked about the fact that it's been renamed. Let's talk about segment routing, the state of it today. Segment routing is a traffic engineering mechanism. It allows a source node to steer a packet through an SR path. And segment routing, you won't hear people talk about LSPs. There are no label switching. There are SR paths. A source node encodes an SR path in each packet, and this alleviates the need for transit nodes to maintain path state. That's the big difference between segment routing and RSVP TE signaled MPLS. In segment routing, source node encodes the SR path in each packet, and there's no need to signal a path from end to end. Today, we have SR-MPLS, fairly mature and being deployed. It encodes the SR path in an MPLS label stack. Each entry in the label stack represents a segment in the SR path. We're starting to experiment with SR and IPv6. And there are two flavors of SR and IPv6. One is called SRv6, the other SRv6+ or SRm6. Both encode the SR path in an IPv6 routing header. This is the IPv6 routing header that's been around for a good 25 years. Each member of the routing header's segment list represents a segment in the SR path. There's a heated debate right now between SRv6 and SRv6+ going on in the IETF Spring Working Group. For those of you who've been following it, I apologize for having blown up your mailboxes. Each has a unique encoding mechanism, and each has a unique approach to network programming and IPv6 extensibility. And we're going to deep dive into that in the next 42 minutes. So, SRv6 preserves the best, SRv6+ preserves the best of SRv6. And there are some things that they have in common. The first is the concept of a traffic engineered tunnel. They share the concept of a path. An SR path provides unidirectional connectivity from an ingress node to an egress node. It can follow a least cost path or a traffic engineering path, and it's defined by the segments that it contains. Okay, we've introduced this concept of a segment. What's a segment? Well, a segment provides unidirectional connectivity from its ingress to its egress, and it's defined by its ingress node and a topological instruction that controls it. So here's where segment routing starts to get a little bit unique, that it has this concept of instructions. Now, what is a topological instruction? Well, a topological instruction executes on the segment ingress node. It defines the segment egress node and the method by which the ingress node forwards the packet to the egress. And there are a few types of topological instructions. One is an adjacency instruction. It forwards a packet through a specified interface. It's strict routing. Another is a node segment. It forwards a packet through the least cost path to the egress node. This is loose source routing. And then there's a binding instruction. The binding instruction forwards a packet through another tunnel. It allows segment routing to be applied recursively. Now, we have one more concept to deal with. Segments are identified by segment identifiers. A segment identifier is the thing that shows up in that routing header. In SRv6+, a segment identifier is 16 or 32-bit unsigned integer. This is a major difference between SRv6 and SRv6+. In SRv6, a segment identifier is a 128-bit entity. It looks like an IPv6 address, but it's really not. It's different. We'll talk about the differences in a little while. In SRv6+, a segment identifier is 16 or 32 bytes. It's a key into a fib that contains the real segment instruction. Because there's a one-to-one relationship between a segment and the topological instruction that controls it, the Cid that identifies a segment also identifies the topological instruction that controls it. This becomes interesting in a while. A Cid has strictly node local significance, just like a well, let's see. What else has node local significances? Well, not global significance. And it's distributed by the IGP. Now, the next concept is network programmability. This is something that SRv6 and SRv6 Plus have in common. We have some instructions that are topological, that force a packet from one node to another. We have other instructions that are not topological. They do other things. And there are two classes of these service instructions. One class is a per segment service instruction. It's executed on each segment egress node. And it does things like expose a packet to a firewall policy, expose a packet to a sampling policy. These kind of instructions are useful for service function chaining. The next kind of instruction is a per path instruction. It's executed on the path egress node. Generally, it overrides the default payload handling rules for IPv6. For example, the default payload handling rule is pop off the IPv6 header and all its extensions and process the next header. An example of a per path service instruction would be decapsulate the payload and forward it through a specified interface, or decapsulate the payload and forward it using a specified forwarding table, maybe a VPN forwarding table, a VRF. Now, a service instruction augments but does not define an SR path. What does that mean? It means one packet can be sent through an SR path with one set of service instructions, another packet sent through the exact same path with a different set of service instructions. Now, let's pull it all together in a picture. Here we have an SR path. It contains nodes A through F. The path contains 3 segments. You can see them AC, CD, DF. Each has a topological instruction and a service instruction, and there's one service instruction at the end of the path. Now clearly, not all SR paths have all types of instructions. The topological instructions are mandatory, the service instructions are optional. Now, SRv6 leverages the IPv6 extensibility model. IPv6, as it was defined many, many moons ago, gave us a bunch of mechanisms for extending it. And SRv6, probably the biggest difference between SRv6 Plus and SRv6 is that SRv6 Plus leverages the extensibility mechanisms of IPv6 as they were defined way back when. So first, let's have a little refresher in IPv6 extension headers. IPv6 defines many extension headers, and they're processed in the order that they appear in a packet. They basically fall into 3 categories: per hop, per segment, and per path extension headers. Per hop extension headers are processed by every hop along the path. There's only one per hop extension header. It's called the hop by hop. Per segments are processed by every segment endpoint along a path. They only occur if there's a routing header in the packet. The per segment extension headers are the routing header and a destination options header that may precede it. And then the per path extension headers are processed only by the egress node, by the path egress node. And there are a bunch of them: fragment, authentication header, encapsulating security, payload, and another destination options. Now, an SRv6 packet can carry any valid combination of IPv6 extension headers, but it leverages the routing and destination options header. And we're going to talk about how it leverages those 2 headers in just a second. Let's have a quick refresher on routing headers. The routing header is used by an IPv6 source to list one or more intermediate nodes to be visited by a packet on the way to its destination. This is from RFC 8200, and it's basically saying that the routing header is IPv6's traffic engineering mechanism. It gives you a loose source routing mechanism, and it has 5 fields in it: A next header tells you the type of the next header in the extension header chain. A header length, a routing type, because there are many variants of routing headers. SRv6 defines one variant, SRv6 plus defines another variant. The number of segments left, that's the number of segments still to be visited along the SR path. And type-specific data. Type-specific data can contain anything, but it always contains a segment list, the list of segment endpoints yet to be visited. Now, how do we process a routing header? Well, the first thing we do is take a look at the segments left field. If segments left equals 0, skip it and proceed to the next header. You are at the path egress node. If segments left is greater than 0, decrement segments left and update the destination address to reflect the next segment ingress node and then forward the packet. Don't process the next header. If you update the destination address, forward to the destination address. Don't look at the next header beyond the routing header. Now, SRv6 plus defines a new routing header type. It's called the compressed routing header. It resembles the generic routing header defined in RFC 8200. It has the same 5 fields, the same simple function. There are 2 flavors of this compressed routing header, a SRh16 and a SRh32. One defines the Cid in 16 bits, the other in 32 bits, otherwise they're identical. And there's a local data structure called the Cid Forwarding Information Base, or the SFIB, that maps this 16 or 32-bit Cid to an IPv6 address and a forwarding instruction. So, what does this routing header look like? Not many surprises. The 16-bit version has the 4 mandatory fields, followed by a list of 16-bit SIDs. The 32-bit version, the mandatory fields, followed by a list of 32-bit SIDs. Now, what does this forwarding information base look like? Well, remember when we're processing the CRH, we look at segments left, it is indexed into the SID list. We find a SID, and we look for an SFIB member that is indexed by that SID. That member contains an IPv6 address. We will copy that IPv6 address to the destination address of the packet. Then we'll take a look at the segment type. It can be adjacency, node, or binding. If it's an adjacency SID, we forward the packet to through an interface that is defined by in this SFIB. If it's a node SID, we forward it through the least cost path to the destination address. If it's a binding SID, we encapsulate and forward. Now, a quick analysis of the CRH. The CRH is used by an IPv6 source to list one or more intermediate nodes to be listed on the way to the packet's destination. There's nothing more, nothing less. Basically, what we're saying in this bullet is that the CRH is used exactly the way RFC 8200 says to use routing headers. There are no surprises here. The CRH is relatively short. If you take a look at routing headers over time, how many of you have ever deployed a routing header in your networks? I see no hands. Well, one reason is because there's not a whole lot of IPv6 deployment, but even for those of you who've deployed IPv6, the reason you haven't deployed routing headers is because they get really long, really fast. If a routing header has a list of 128-bit segment identifiers in it, it can get to be 56, 64 bytes, really long. That's ASICs unfriendly, it consumes a lot of bandwidth. It's one of the reasons the routing header never really took off. Well, we've compressed the routing header, so you can fit a fairly long path into 24 bytes of routing header. This is ASIC friendly, and it doesn't consume lots and lots of bandwidth. And by the way, that's one of the big differences between SRv6 Plus and SRv6. SRv6 Plus, one of SRv6 Plus's biggest selling points is this compressed routing header. Okay, while we're doing our look back at IPv6 extensibility mechanisms, we'll take a look at the destination options header. Destinations options header is used to carry optional information to be examined by a packet's destination nodes. And a packet can carry two destination options header. In fact, in RFC 8200, there is only one extension header that's allowed to occur twice in a packet. That's the destination options header. It can occur once preceding the routing header, and that one is processed by every segment endpoint, and it can occur another time before the upper layer header. That instance of the destination options header is only processed by the path egress node. Now, SRv6 defines two new options. One is the per segment service instruction identifier. It's encoded in a destination option that precedes the routing option header, which means it's processed by every segment endpoint. It identifies a service chain. Each node learns the function that it executes in the context of that service chain from a controller, and it has network-wide significance. This IP option is an optional option. What does that mean? The first two bits of an option identifier tell a processing node what to do if it does not recognize this particular option. The first two bits of this option are 0, which means if the processing node does not recognize it, just skip over it, process the next option or the next extension header in the packet. So it's an optional option. SRv6 Plus defines another option called the per path service instruction identifier. This is encoded in the destination option header that precedes the upper layer header. It's processed by the path egress node. So the distinction between the two. One is, the first one is processed at every segment endpoint. This one is processed only at the path egress. It identifies a per path instruction. It has node local significance. It's advertised by, allocated and advertised by the processing node, advertised by BGP. It basically replaces an MPLS service label, something that you would have seen in L3 VPN. Its processing is not optional. If a node sees this, it must either recognize it and process it or drop the packet. Now, SRv6 Plus avoids some of the pitfalls of SRv6. And let's talk about some of the pitfalls of SRv6. SRv6 modifies the semantics of an IPv6 address. The destination address field, in SRv6, the destination address field can contain either an IPv6 address that identifies an interface the way RFC 4291 says it should, or it can contain an SRv6 SID. SIDs are copied from the routing header to the, in SRv6, they're copied from the routing header to the destination address. Now, a Cid semantic is different from an IPv6 semantic. In SRv6, the high order bits of a Cid represent the locator, and the low order bits represent a function and arguments. So what does a Cid represent in SRv6? Well, it is a function instantiated on a node. The node is identified by the high order bits, the locator. The function is identified in the low order bits. So what I did with a topological instruction and put in a fib and distributed in what SRv6 did with a instruction and put in a fib and distributed with an IGP, SRv6 encodes in an IPv6 address. Basically, they're using the low order bits of an IPv6 address to tell the processing node what to do when it receives a packet. This is kind of a subtle point, so I'll try to articulate it one other way. In IPv6 and SRv6+, an IPv6 address means exactly one thing. It identifies an interface, period, end of story. In SRv6+, an IPv6 address identifies an instruction to be executed on a node. The address isn't the destination. The address represents what should be done with a packet once it reaches the destination. In my opinion, redefining something as fundamental as an IPv6 address is kind of a dangerous thing to do. Lord knows how much of the internet relies on the semantic of an IPv6 address. Whoops, wrong direction. Let's see. And we've already gone over this. The next issue is SRv6 couples topological and service instructions. You remember in SRv6+, we put topological instructions in a fib, and that fib is referenced with a routing header. So the routing header does nothing but traffic engineering. In SRv6+, we've put both topological and we've encoded both topological and service instructions in an IPv6 address, and we made a stack of them in the routing header. So in SRv6, both topological and service instructions are encoded in the routing header, even though IPv6 provides a destination options to encode service for the specific purpose of encoding service instructions. Now, what happens if an instruction gets bigger than the low order bits of an IPv6 address? Well, then we have to start expanding that routing header. SRv6 defines a routing header called the segment routing header. It has more fields than the compressed routing header. It has tags, flags, and TLVs. When all the information you need for to process a packet can't be fit in the low order bits of the address, they start building these tags, flags, and TLVs in the segment routing header. This means the segment routing header is going to contain more and more information. Given that this will need to be processed by ASICs, that's probably not good news. Also, new security mechanisms are, this coupling requires new security mechanisms. The routing header can't be protected by IPv6 authentication or ESP headers, so they've had to define a new SRh HMAC TLV. The next issue is difference between SRv6 and SRv6+'s routing header size. We talked about the big benefit of SRv6+ as being able to fit lots of SIDs in a small routing header. Well, here, let's say you have a fairly average path with maybe 5 segments in it. In SRv6, you need an 80-byte routing header to encode that. In SRv6+ with 16-bit CRH, you only need a 16-byte routing header to encode. Okay. At the last IETF, there was a proposal to reduce the size of routing headers for SRv6. And that proposal introduced a new SID type called the micro-SID. The micro-SID modified IPv6 semantics even more. Basically, the way it works is a network operator obtains a /32 for micro-SID processing. So let's say he gets 201 db8/32. Then from that /32, he assigns a /48 to each node. Now, the path for any, from node 1 to node 3, let's say the path to node 1 via node 3, and node 2 is represented by the 32 followed by the unique 16 bits of each. So it's represented by 201 db8 321. Then as we go from path to path, from node to node, you shift 16 bits of the address. I won't read through the slide because it's fairly complicated, but you'll see what we're doing. We're basically changing the address to make the path work. This is clearly changing the semantics of an IPv6 address, something you probably don't want to do. So there were some impediments to deploying this this microSID. First is you have to obtain a /32. Second, the network operator has to maintain a specific numbering policy in order to make the solution work. For instance, if a /48 represents a microSID, you better not advertise anything more specific than that /48, or else you create black holes, and it further modifies the IPv6 addressing semantics. So let's take a look at the implementations and deployments of SRv6+. There's a POC implementation of SRv6+ on Linux with Juno CRPD. If anybody's interested in playing with it, contact me later. There's an MX POC to be complete. Let's see, maybe completed by time of Nanog presentation. We didn't make it. It's going to be another 4 weeks or so. Liquid Telecom has done a implementation with their data plane developers kit, and they've also demonstrated interoperability between the Linux and DPDK implementations. Liquid has also done an experimental deployment in their network, and there'll be more deployments coming in the next few weeks. So what conclusions do we have here? SRv6 preserves the best of, SRv6+ preserves the best of SRv6. It's traffic engineering, it's network programmability. But SRv6+ is more deployable because it defines as little new protocol machinery as possible. Instead of deploying new protocol machinery, it leverages relevant and available IPv6 extensibility mechanisms, the routing header, the destination options header. And it doesn't attempt to redefine fundamental IPv6 concepts, like the IPv6 address semantics or acceptable use of a routing header. Thank you, and do we have any questions? Yes.
Hi, Lee Howard, IPv4 Global. Thank you. This is always interesting. I'm not even subscribed to Spring. I'm on 6-man, and that's been busy enough. And just talking about the semantics here. I'm not terribly worried about redefining certain semantics within IPv6 addressing, because it seems to me that the last 64-bit. You said, well, we know what a host is. It defines an interface. When I was in the IAB, we kept grappling with what is an endpoint? What does that even mean? Defining a service as an endpoint, that ship sailed. We've already got that. Now, when you get to /48s, yeah, sure, that's a big deal. So you talked about the implementation, the proof of concepts that already exist. You specifically mentioned Liquid Telecom's DPDK. Is that the DPDK that I'm familiar with, that I've used before, or is that a proprietary?
No, it's the one that you've used before. They've just implemented over it.
Okay, so they're using the well-known DPDK,
yeah,
and they're implementing their own stuff on top of that. Cool. And I'll ask Andrew, for his particular details. Thanks.
Okay.
Hi, Ron. Phil Bedard from Cisco. So I had one question. I've been following the Spring and the 6-man working groups, and it seemed like they concluded with moving forward with the original SRv6 architecture and completing that work. I guess, where do you see the future for M6 in the IETF and how that's going to progress?
Well, we're clearly going to keep pushing it with the customers who've shown interest. And we're hoping that I can't speak for the Spring chairs or the Spring AD. We're hoping that they will follow along.
Okay, thank you.
Hi, Rob Kronk. I'm from Ball State University. I kind of have two-part questions. My first, I want to preface, I really appreciated this presentation. IPv6 is going to be huge, especially in my lifetime. But one thing I'm kind of weary on is you mentioned that SRv6 or SRv6 Plus, one of its biggest benefits is it's going to be compressing that routing header to a much more manageable size. What happens when you implement that on a large-scale network and the routers are dealing with several packets with this compressed router head? Won't it still face the same issue that SRv6 has? It's still going to slow down the network?
There's an engineering trade-off. And the trade-off is between the size of the extension header chain and an extra lookup. One thing you can do is put the entire instruction in the routing header. If you do that, you get a really large routing header chain. And what you need to do at the beginning of every packet, at the beginning of processing every packet, is copy the packet from packet memory into ASIC memory so you can do it. That's expensive. Another choice you can make is compress the routing header chain. So what's in the routing header is an index to a fib entry. Now you have a short copy and another lookup to do. As it turns out, the short copy and another lookup is more friendly. You're better off doing the short copy and another lookup and having a short routing header than having a routing header that goes out to hundreds of bytes long. Because there are two reasons you don't want a really long routing header chain. One is the ASIC issue. You don't want to have to copy lots and lots of bytes from buffer memory into ASIC memory to process. The other is overhead. In the internet today, packets tend to be short. I think one of you folks can probably give you a better number than me, but the average size of a packet in the internet today is 500, 700 bytes, something like that. Anybody have a better feel than that? Well, in a world where the average size of a packet is 500 or 700 bytes, 100 bytes of extension header overhead is just unacceptable. So much better compression.
Thank you for that. My second question is more so on the opposite side. So one of the things I'm currently learning in my master's program is software-defined networking. I don't have too much of a grasp on it. I don't want to, it could be answered, whatever. But I know one of the biggest benefits of it, it allows for dynamic networking. And one of the points you made was SRv6 Plus effectively lets these nodes learn dynamically what they need to do in the network. So what would you say SRv6, what implications does that have for a software-defined network in the next 5 to 10 years?
Okay, we talked about something called an SFib. The SFib translates SIDs to IPv6 addresses and the actions associated with the SID. Right now, we're distributing that SID information in an IGP. You could distribute it from a controller just as well. The service instructions, the per path service instructions, right now we're talking about distributing them with BGP because the machinery is there. You could distribute it with a controller just as well. Service SIDs, the ones that are executed at every segment endpoint, those will almost certainly be distributed from a controller. So putting the smarts in SIDs that are distributed from controllers to network processors, that really facilitates software-defined networks.
Yeah. Thank you.
Hi. Are we reintroducing the need for state within each node with SRv6 Plus?
I'm sorry, the question again?
Are we reintroducing the need for state within each node?
Good question. This is very insightful. Segment routing got rid of per path state. There was no longer a need to signal per path state information, RSVP, LDP. In SRv6 and SRv6+, we still have no per path state. What we have is per segment state, and lots of it. It turns out the amount of per segment state maintained in SRv6+ is almost identical to the amount of per segment state maintained in SRMPLS. How do I know that? Because the state is signaled by the IGP exactly the way it used to be, and the TLVs used to signal SRv6+ state are a subset of the TLVs used to signal SRMPLS state. In fact, when I wrote the ISIS extensions document for SRv6+, I basically did it by cloning the SRMPLS document, changing the names of a few TLVs and deleting a few others. So yes, there is per segment state. No, there is no per path state.
Got it. So it could be a hybrid, right? I could have a very dumb middle, right? And at the edges where the ingress and egress, I could have a node that basically understand the state.
Nodes understand state, well, a node understands the state for the segments in which it participates. It does not understand what paths pass through it. It has no idea what paths pass through it. And this is true for SRMPLS, SRv6, and SRv6+.
Okay, thank you.
I'm trying to wrap my head around what it'll be like to diagnose behaviors in a network like this. Do you have any comments on that?
Okay.
And in particular, the two schemes, like, what will be explicitly visible in a packet that I source versus...
Okay, the questions are how do OAM work? In SRv6+, OAM works pretty much the way it does in IP. And the reason why is we haven't changed the semantic of an IPv6 address. Traceroute still looks like traceroute. Now, granted, when you look at the original packet in the traceroute, you will see a extension headers, just the way you would in any other IPv6 traceroute. Ping still works like ping. Now, in SRv6, you need new OAM mechanisms. If you send an ICMP echo request to a 128-bit entity that is a Cid and not an IPv6 address, you won't get an echo reply back. You'll get an ICMP parameter problem message back. So SRv6 compensates by creating new OAM mechanisms. These just aren't needed in SRv6+. It looks like IP and IP encapsulation.
But isn't there a trade-off there, right? These SFibs, which are local identifiers, right? So, the context of what's going to occur to my packet is not totally encoded in the packet at source, right?
Well, traceroute will show you what happened. At every hop, it will show you which Cid translated to which IP address. But yes, there is a level of indirection, and with every level of indirection, a new level of complexity. Any more questions? Well, thank you very much. If anybody wants to corner me with, oh, one more coming? No, not one more coming. Okay, well, thank you very much.